All good? Okay. So I'm going to talk about work that has been done in the last year with Jordan, Christian, Stefan, Amir, and Max in these two papers. So the first paper is on the topic of this talk, quantizing Carrollian field theories. The second paper has a bit of a different focus. It's not completely unrelated. And we talk about 3D gravity, and it will appear only as a kind of an example in this talk. So, but if you're interested in more details, Stefan gave a talk about this in the celestial holography seminar series, and you can learn more about 3D gravity in our approach in this seminar. Okay, so we all know that light-like structures provide interesting information. Also, already Galilei understood this, and but now in this conference, I think we're more interested in null surfaces. There are a lot of interesting null surfaces, null infinity, black hole horizons, killing horizons, many interesting structures. What all of them have in common, as Luca was mentioning yesterday and already at a couple of other points, is that they all have non-Lorentzian geometry. So on each null surface, there's defined what's called a Carroll geometry, which is given by this pair of a degenerate metric and a vector field, a nowhere vanishing vector field lying in the kernel of the metric. So already at this point, you can formulate the question that I want to address in this talk, which is, can one define quantum field theories on such spaces? These are very different from the quantum field theories that we usually work with, which are defined on a Lorentzian or Euclidean background. So you might expect that they are very exotic. And the takeaway message that I already want to give you is that it seems you can do this. It's very subtle, but it's, and this is the main message of this talk, it's very difficult to obtain non-Gaussian dynamics. Okay, so to be more specific, why are we interested in these null surfaces? So the question I posed on the last slide was a bit academic, but of academic interest, but here there's a very concrete reason, namely on null infinity. As you all know, there's a conformal Carrollian structure. So it's a bit looser than what I said before. And there you can phrase now the question that has been discussed in the last couple of years, namely, is there kind of a holographic description of, say, scattering in 4D asymptotically flat spacetimes in terms of a 3D boundary theory coupling to this conformal Carrollian geometry on scry. Now, what are the expectations that we have? So this is a major research question by now, I would say. So what are the expectations that we have of this holographic dual? So it should reproduce, first of all, scattering amplitudes. You might expect that the scattering amplitudes are reproduced as correlation functions of this theory. And so it was shown in these two very nice papers that indeed by an integral transform, you can convert scattering amplitudes in momentum space to objects which transform in the correct way. So they transform indeed like you would expect conformal Carrollian correlators to transform. What you find if you apply this integral transform is that you have the amplitudes that you get are time dependent. They can become very complicated, or these correlators can become very complicated. They are time dependent, and low point correlators. Sorry, they should be correlators. They are distributional. So 2, 3, and 4 point correlators are distributional for the same reasons as in celestial holography due to momentum conservation. So we should be able to reproduce these time-dependent distributional correlators, but there should also be some trace of the soft sector that we know that gravity in asymptotically flat space has, which has a very rich soft sector, and for this soft sector, we expect to have these time-independent correlators. For instance, this was determined in this paper here. You can write down this is the correlate of the Goldstone boson of broken supertranslations. And you see, as you see, it's time independent and lives just on one slice of scry. It's also divergent. Yes, indeed. There's a huge IR divergent in front of it that, I mean, I didn't keep track of it. I should have put it here. Right. So there are also IR divergences here, and this actually resonates a bit with what I'm going to show later. So for scattering, yeah, so this is something that is always confusing. I had some discussions yesterday also about this. I think for scattering amplitudes, I guess you can just add an additional label to these points, plus, sorry, to these fields, plus and minus. And then you want this thing to be non-zero only for plus, minus, where plus and minus denotes ingoing, outgoing. I want to, exactly, I might want to put a plus here and a minus there. And plus plus should be 0. Yeah. I think if you're just studying scattering on flat spacetimes, on Minkowski space, you can introduce a coordinate u that covers both square plus and square minus.
This is, maybe I could comment that these peculiar quantum field theories are in a sense associated to the peculiar that are the conformal particles, because ordinary conformal particle, not tachyonic, doesn't move. Therefore, the corresponding Marshall condition simply is E squared minus M squared equal to 0, and this should give a very trivial equation of motion.
Yes, yes. So you're saying the Carrollian particles, you mean they
Yes.
don't move? Yeah, yeah, I agree with this. Yes, yes, yes. We'll see traces of this later.
U is the time variable.
U is a time variable on scry. Yes.
It's in 4-dimension space-time or in 3-dimension.
This is a it should be a 3-dimensional correlator living on scry, and so you have. Sorry, this is scry. Here we would say that there's a time coordinate u, but the way we want to think about this is now as some kind of. I mean, it has r times s2, where here we have spatial coordinates xi, and then here there's a time coordinate u running up and down. But on this, so this space r times s2, there's a Carrollian structure defined of it. It's not it doesn't have a Lorentzian metric. I guess in Minkowski space you can just shoot a light ray through it, but as long as if you're not in Minkowski space, it might be a bit more tricky. I believe that. Yes.
We certainly, the conformal structure of the sphere is not star plus, it's locked to the conformal structure star minus. So there is a match of an angle on the sphere on star minus with an angle on the sphere the star plus, but it seems that the memory effect would make it very hard to relate u equals 0 to b equals, which is what we need to do. One might worry that equation very on how that will be unfolded.
Sorry, what was the last statement in perturbation? It would be changed if you go away from perturbation theory, or how you see it in perturbation. Okay. Right. Yes, let me think about it. I mean, I agree. I'm always confused about these things. In scattering amplitudes, I don't see. So if you just write down scattering amplitudes and correlators, I don't see such a problem. But yeah, yeah, right. But yes. Yeah, it's. I mean, perhaps if some other Carrollian holographers have yeah.
Yeah. That, speaks to in all the factors that we have bad position on street. I can see, but all of the you use the different you all that. Well, I guess another way of saying it's just antithetical to pure GR identify the point value on CR.
Yeah. Yes. Yeah.
So maybe going in that direction, it seems that this is suggesting that maybe you want to have some explicit goldstone parameter sitting also in these 2-point correlation functions. That's what, instead of having just U1 and U2, you have a U1 plus C, parameterizing the fact that these coordinates can be super translated with respect to. That's right, some C, some parameterized by some goldstone, something like this. Well, that's a possibility, I don't know, but well, I'm thinking of this because typically, actually, BMS field, like as unitary representation, they would have, in general, an explicit C parameterization. They would not just be a UX object, but also carry an explicit goldstone. So you could maybe imagine having 2-point function with explicit apparition of vacua on top of these other labels. That would make everything much more complicated, of course, but maybe that fits into this remark. Yeah.
Okay. Yeah, as you can see, I'm also myself confused about this. I mean, I would be very happy to talk about this. I'm curious. Yeah, maybe.
As long as the mic had happened to be passed to me, I'm in agreement with what I understand Andy to be saying. And I mean, if you're in flat space time, then if you take a point on scry minus and look at its future light cone, I mean, that'll correspond to a null plane, which will correspond to the past light cone of some point on scry plus. So you would have an identification in flat space time, of a time, a time, at an angle on scry minus with the time at scry plus, but that would be very special to flat space time. Otherwise, these light cones will have caustics and won't do anything nice by the time they get to scry plus.
I agree.
But I think if you work with GR for you to consider the Carrollian CFT as maybe on both and then you have this modal matching, I guess.
Yeah, so this is right. This is so what these authors here, I mean, Romain and Laura and Yannick and Adrien, they considered. I mean, sorry if I summarize your work now, but that you have these two scries glued together at some point where n vanishes, where n the normal vector vanishes, and then here you want to have some boundary condition, this antipodal matching. Yeah, that's the idea in full GR. I mean, as you're saying, yeah, but okay. I think there's still something to understand here. Even I mean, how to do this in perturbation theory is also not so clear, right? I mean, So for the point of my talk, let me just say I will be interested in such correlation functions of fields defined on some Carroll surface. Maybe they have some additional label. And so I will be exclusively in this perturbative setup on Minkowski space. It might be that, as Andy was saying, all of these amplitudes end up to be zero in the end due to the IR divergences. But this is okay. Actually, as I want to show, or as I want to discuss a bit later, this I will go to a more simple setup in a minute. Okay, so now what we know about this potential dual or any Carrollian CFT, if you want, relies on using symmetries of the CFT or on using the dictionary basically the other way. So you can come up with some OPE of this Carrollian CFT by taking the collinear limiting of scattering amplitudes and apply the map, or you can just apply symmetries, see what you get. You can also look at correlators from the small C limit of a relativistic CFT, or you can learn something about the stress tensor of these Carrollian CFTs by coupling them to some geometric background. But the problem so far is that it's very difficult to find some Lagrangian models of a CFT. I mean, this maybe is not very surprising because also it's very difficult for usual Lorentzian CFTs, right? But at least we know there are some that you can write down and you can quantize them, and you can do perturbation theory and check that that it coincides with what you get from the bootstrap, say, right? I mean, you can attack these CFTs, Lorentzian CFTs, from two different angles: perturbation theory on concrete models and more general arguments. Here it seems that at the moment we only have these more general arguments. It would be very nice to just have a Carrollian CFT where you can just do perturbation theory and see whether you really get these structures here, something that looks like this, even if it doesn't have anything to do with a potential dual to gravity, right? So our approach then is just to take a step back and just look at some non-conformal Carrollian theories, where you can easily write down Lagrangian formulations, as I will show you in a minute, and then do perturbation theory and see what kind of structures do you get. Can you reproduce some of these things that we saw in this last slide? So in some sense, we should learn first quantum field theory before studying CFTs. Let me just mention that we're not the first to do this. There were at least two other papers discussing this. What we try to do is generalize and draw more general conclusions. Okay, so this is the outline of my talk. After this extended introduction, I want to introduce these theories. So in general, not from the Carrollian field theories, we'll see that there will be two types of Lagrangians you can write down: or let's say actions you can write down, electric and magnetic theories. And then if we come to it, I will at least tell you of one particular application of one of these theories to 3D gravity. Okay, so let's go into the details. What is a Carrollian theory? We have the Carrollian symmetries, which arise as the C to 0 limit of the Poincaré symmetries. So in particular, you find now that boosts commute and the Hamiltonian commutes. The Hamiltonian becomes central. This is geometrically realized as I told you, as this pair of what's called structure. And if I choose now H to be a flat Euclidean metric, and I look at the Killing vectors that preserve this structure, I will get this Carroll algebra plus an infinite number of super translations. As Luca was mentioned briefly, or just touched upon yesterday briefly, is that if we want to kill these super translations, then we have to add, in addition, a connection. Now, so much about the symmetries. You can give a nice criterion in field theory, which is that if the Hamiltonian density commutes with itself, then you can show, this was discussed in this by Mark and Claudio Teitelbaum and Patricio, that this implies Carrel invariance. So you should compare this, of course, with the Lorentzian case, where H does, of course, not commute with itself. So if we find such a Hamiltonian, we immediately know that we have a Carroll invariant theory, and we can start trying to see what we get when we quantize it. So in particular, we'll be, let's write an action field, the field and its momentum, the Hamiltonian density. And then we see we can have, there are two simple choices if we want to have Carroll invariance, namely, let's just drop pi from the Hamiltonian. Then H depends only on phi, will of course commute with itself and give us a magnetic Carrollian theory. On the other hand, we can also come up with H's that depend on pi, and some combinations of the field itself. Of course, it should not depend, or you can show that it should not contain a gradient term, like the nabla phi squared should be absent. Then it will also commute with itself. Both of these theories can arise as the z to 0 limit of a relativistic theory. However, the more general theory is, of course, like a combination of these two sectors. Okay, so let's study the electric Carrollian theory in detail. So for the purpose of this talk, let's focus on simple two-derivative scalar theories with this action. Can have some arbitrary potential. You can study more complicated models. This is what we do in the paper. But to make the point, this is enough. So the symmetries of this model, they have are global Carrollian invariance. You see it couples only to this n, and there's of course also a determinant of the metric. Sorry, not of the metric, but there's a volume form which is also Carrollian invariant. It's invariant on the super translations, and it actually has much more symmetries, maybe more than we want. It has also volume preserving diffeomorphisms. In the end, maybe we want to kill them as well, but this will become a bit tricky. I will mention this a bit later. So let's take the simplest example you can think of, just a quadratic potential, and apply canonical quantization. You find that immediately that all the states that you get have the same energy, right? There's no k squared in the dispersion relation. So what you get is, instead of these hyperboloids, you get flat bands. And this is what Kim was referring to before, that the energy of these particles is just, I mean, this is the dispersion relation of these particles is very simple. So we get these flat bands, and if you look at you can compute the free energy. It looks the same as for the usual bosonic theory, but now without the k squared. So which means that this integral just factors out, and you get a huge UV divergence going like a to the minus d, where a is some small distance cutoff. Similarly, in perturbation theory, for all, due to the absence of the k squared term in the propagators, all of these propagators, all of the loops will diverge like a to the minus d. So you get a huge number of divergences that we have to deal with. So you have to regulate the theory, and here's the way that our prescription to do this. There might be other ways, maybe smarter ways than we do it, but this is what we did. So what we're doing is just the simplest you can think of. We put this on a spatial lattice. So we write the action as a sum of a lattice points, where on each lattice point now we have a scalar field that is, so this is the action for this scalar, so it's not for this scalar on this lattice point. Notice very importantly that I had to rescale in order to write the action like this. For one lattice point, I have to rescale the field by a to the minus d over 2. There's an overall factor a to the d here that you have to get rid of in order to write it as a sum over of like well-normalized actions on each point. Here's the second assumption. We assume that on each lattice side, there's a finite potential in terms of these tilted fields, right? There's a, we can just write down the potential. And then now we can just do perturbation theory, right? We can compute correlators of the tilted phi fields on each point. You see, of course, that they're restricted to one point. I mean, this is just quantum mechanics. You can do perturbation theory. And for any coupling you will choose here. So for instance, the 2-point function, you get an expansion in terms of Feynman diagrams. And at each order in perturbation theory, 2-point function will be corrected by any lambda you put in here. Yeah.
Sorry, just to be clear, in this theory, no matter what you do, wait as long as you like. One point here on the sphere is never going to talk to in any way,
Yeah.
even Another point arbitrarily close.
This,
And
right.
all of this stuff is just regularizing all the divergences you're getting from the delta functions you'd have in the continuum to do that.
Yeah, I completely. I mean, this would be the outcome. Yeah. But it would be even worse than that, I believe. Let's wait a minute. So we have this 2-point function. You can also compute 3-point functions at each lattice side. There will be non-zero on each lattice side. But however, now let's go back to the continuum prescription. And what we'll see, of course, is that for the 2-point functions, all of these delta ij's that we have will, or maybe let me just finish this. All of these delta ij's will combine into delta functions on each point, and the 2-point function that we'll get will be corrected at each order in perturbation. Yeah, sorry, Andy.
Well, so there's two fields, phi plus and phi minus, as you said earlier.
Now, okay, now I'm in a kind of abstract setup that has nothing to, or has not much to do with gravity. It's just an abstract field theory on a Carrollian manifold.
I see.
Yeah.
But it's motivated
It's
by
motivated.
getting scattering amplitudes of gravity.
I mean,
And then we would only expect coupling between phi plus and phi minus, and that would maybe hopefully be the answer to David's question, that there could be non-local, because you don't expect it. You can't scatter particles from scribe plus to scribe plus. So there's stuff on scribe plus and stuff on scribe minus, right? And
yeah.
no.
But okay, this is. I think that the problem that you were referring to was really in this more abstract setup. But yeah, if we were talking about scattering theory, then we would like to have two families of particles, or two flavors of particles where only plus and minus talk to each other, and the propagator should be off diagonal in this space. Yes, but then I mean, we still would expect to have the 2-point function, but the 2-point function we would still expect to have non-zero 3-point functions in this case, right? Between plus, minus, say. So in this setup of just one scalar field, this is not what we're going to find. In this setup of this one scalar field, the only thing that we have, so the 2-point function, it gets corrected at each order in perturbation theory. So what we get is a finite ultralocal 2-point function. However, all the 3-point functions, they vanish, right? Even you could expect that there might be delta functions sitting at each point, but it's actually set to 0. So it's somehow, that's what I meant, it's worse than what you were saying. That this 3-point function is 0. 4-point function is 0. Everything is 0. Only the Gaussian correlators remain. So we found a way to regulate these divergences in a way that electric Carrollian theories produce nice 2-point functions that get corrected at each order in perturbation theory. However, we can only describe generalized free fields. And I would say that as far as I'm aware of, there's no other way of I haven't seen a work where you're able to find, where you're able to find finite correlation functions and you have a non-vanishing 3 or 4-point function as well.
I don't quite understand this. So it looks to me like when you've regularized, you've just got, however many lattice sites you've got copies of quantum mechanics along the U direction.
Yeah.
So for each lattice point on the sphere, you've got a quantum mechanical system moving in the U direction.
Right.
Okay, I can certainly have interesting correlation functions in quantum mechanics.
Yeah, right. I mean, this is what I have here, right? I can have an interesting correlation function on each lattice side, right? I have delta ij, delta jk. This is an interesting correlation function, but it is due to this rescaling that we have to do in order to go back to the continuum field theory that all of these vanish. It's just, it's just you just have to count. That's just a scaling argument. If you right on each lattice side you have this, but if you want to, this is why I said this is important. If you want to go back, turns out that these powers of A, they don't allow you to transfer this into enough delta functions. To delta function.
rescale the couplings
Yeah.
in some way to absorb
You-
that? I mean,
You can rescale. So, right, our prescription is, if you want, you take the naive continuum Feynman rules with C to 0, and for each coupling constant that you have, you want to rescale the coupling constant by positive power of A. This way, I mean, you already expect that, I mean, 3-point functions, an endpoint function will be 0, right? Because the coupling constant is, if you send A to 0, it vanishes. But in the 2-point functions, everything, all the deltas combine in such a way that the 2-point function still is, gets renormalized in each order. I guess what you might want to do is you want to add negative powers of the coupling constant. I mean, you might want to renormalize the coupling constant here with negative powers of A, but then the 2-point function will blow up. I mean, there seems to be like some tension to have a finite 2-point function and finite higher point functions, at least in this regulation scheme. But okay, maybe there are more smarter ways to do. Just that it seems to be very tricky to get something, let's say, interesting if you define interesting by non-Gaussianities out of these theories.
hang on, sorry. Sorry to keep interrupting. So classically, by doing this rescaling, you can have perfectly fine interacting series. But the problem came when you also wanted to have a finite one-loop correction to the 2-point function.
Yes.
Yeah, I see. Yeah, that doesn't surprise me at all because everything's ultra-local. So it's.
Okay, so notice that's also like a curious point. We have to specify. I have to tell you what exactly all the couplings on each lattice side, in order just to obtain the 2-point function of the continuum of field theory, right? Many couplings as you wish of the kind of the UV theory in order to get some IR quantity, the 2-point function. I mean, here, IR is a bit of a fake because it's also just localized on one point, but some people might want to call this a UV-IR mixing. Okay, so also this naive rescaling that you want to do actually breaks down if some additional cell points can contribute that are not there in the original Lorentzian limit, then it's not enough to just rescale these couplings. So we demonstrate this on the case of the compact Carrollian boson, where you have additional saddle points in the Carrollian case that you don't have in the Lorentzian case, and that these will contribute. And then, so I was mentioning before that these theories actually have too much symmetries, right? They are in some sense too restricted. So what we might want to do is we want to break these volume preserving differentialisms. And you cannot do this with just such a term. You have to add more complicated terms, and it appears that the simplest choice is to add a potential that is quartic in derivatives, which was done in these two papers coming from very different angles. So maybe what you want to do is you want to quantize this theory, and you might get something more interesting. However, we didn't find a good way to do this. So again, some divergences that we didn't know how to deal with, but this might be an angle of attack to find something more interesting. Yeah.
Are you going to say something about quantizing tachyonic Carroll?
I don't think so. No.
But that will suffer the same difficulties. The particles will move.
I don't know. I think I don't even know what this means. But yeah, maybe we can discuss later. Yeah. Yes.
How do requirements are in the
Well, I mean, we have not in generality. I don't see any issue here at this point, right? We have just some quantum mechanics at each lattice side with a unitary evolution by some Hamiltonian. But we didn't discuss this in more. If you have something to say, I would be interested to it. But okay, yeah, but yeah, we didn't think about this in a more abstract way. Okay, so this seems to be like an open problem. We want to define an interacting electric Carrollian QFT. And even better, we want to have a conformal Carrollian QFT, right? If there's any way to make sense of the Carrollian conformal Carrollian proposal, we should have, I mean, there should be a way to define these theories, right? I mean, it would be strange if there were only some very abstract arguments and you can never write down an explicit theory. Okay. Having said this, let's go on to the other topic, which is the magnetic Carrollian theories. Okay, here's the magnetic Carrollian action. It looks very different from the other case. So this is what I called, this is the momentum and the field Q and chi. Here, as I said before, the Hamiltonian density now only depends on the field on chi. Will obviously commute with itself at each point. Symmetries are that this is Carrollian invariant. It's also super translation invariant. And if you vary with respect to Q, you immediately see that on-shell chi is constrained to be time independent. So this is already very nice. We expect this, as I said before, corresponds to one of the expectations that we have, that there are sectors with time independent correlation functions. And it looks like these magnetic actions can do this. Now we can write down some basis of states with this inner product, very similar to the usual quantum mechanics, where you just have some continuous set, I mean, the X and P basis, if you wish, but now only delta functional normalizable. This is a bit abstract, but maybe if I go to the gravity case, yeah, let's see. Some cases you can make this path integral a bit more well-defined. These are, of course, energy eigenstates, and we'll have a continuous spectrum of energies, so we expect to have some IR divergences in the same way that you have IR divergences if you, yeah, right. We have a continuous spectrum. We'll see the IR divergence in a minute. So let's have a look at the partition function. This is the usual definition of the partition function. We have some the Hamiltonian operator, the trace in this basis that I chose here. So this is the basis, and since these are eigenstates, the only thing that we'll get is a big IR divergence from this delta functional that is completely independent of the model, and some path integral over the chi's weighted by their energy. So this looks very much like a partition function of a statistical system in one dimension lower. You can compute correlation functions or thermally distributed correlation functions of this model very easily. You can also compute these Q correlators. But what you will find is that these correlation functions, due to the fact that this is on-shell required to be 0, they're all time independent. So the upshot of this is that the magnetic Carrollian theories, they behave like systems of codimension 1, and they yield time independent correlation functions exactly as we would like. I mean, and this is one of the features, as I mentioned in the very beginning, that we would like to see emerge from a conformal Carrollian theory, right? So it looks like these magnetic theories have something to do with the soft sector. Okay. Now, as I said before, it's difficult to get, if you have a purely electric theory of some scalar field, it's difficult to get some interesting quantities out of it. So maybe the models are just too simple, and we should couple magnetic and electric sectors. So here's a very simple model of just some free massive electric scalar field coupled to some magnetic scalars with a Yukawa interaction. In the paper, we also discuss some another model. You can also discuss Carrollian electrodynamics coupled to a scalar field, but the conclusions are very similar. So you can regulate the divergences on the spatial lattice. You introduce some finite temperature also because it gets rid of some of the divergences along the way in the computation. You do perturbation theory, get some Feynman diagrams, some slightly complicated looking results. However, if you take the continuum limit in the very end, a to 0, beta to infinity, again, all the non-Gaussianities go away. So only Gaussian correlators are left, which is, yeah, just again a bit disappointing.
Sorry, why do you have du of chi?
Sorry?
Maybe I misunderstood. I thought chi was U independent because it was magnetic, but you've got du of chi?
Yeah, I mean the correlators of chi will be all time independent.
Oh, I see. Q just.
Q is a Lagrange.
Sorry,
I agree. Yeah. So maybe this is so. If you look at the Hamiltonian, so the Hamiltonian is just this term, and this term without the du chi. Then you see that everything chi just commutes again. So chi, if you want, is just some statistical background. So you can choose a basis for the fields where you have the chi field and the psi field, which contains, I mean, there's a basis for the phi, a bit abstract, but I mean, it's just.
Yeah, in these correlators, did you add any non-trivial? I mean, do you still have delta U, U1 minus 2, these sort of things, or can you have non-trivial, interesting interactions between fields at different points of space?
For the chi?
No, sorry, delta. I mean, can you have non-trivial 2 or 3 or whatever point functions for fields which are different points of space for phi? Do you have everywhere delta and X?
I think here okay. I don't want to say something wrong. I think here you will always have a delta function here, but let me check. I'm not entirely sure. Let me. Okay. Okay, I will tell you later. I'm not entirely sure. I think you still always have a delta function there. Okay, so going back to this case, so what you find here is that you basically have some effective quantum, going again to these lattice regulations, you have some effective quantum mechanics for phi on a background of these chi fields that is thermally distributed. Now what you can do is, I mean, just prove something that's kind of cute, which is the following. So take the density matrix, but send beta to infinity. So what this does for you is that since our field phi is a massive field, it will go to the ground state. So this is what I mean by this. So this density matrix will project to the ground state for the phi in some background for the chi fields, where the background has some weight that comes from the Hamiltonian. So I can also write this like this. So this is the expectation value of the projector to the ground state of chi in some thermally distributed chi background. And so what you can show now is that the zero mode of Q, if I apply this to any functional f of the fields and do this limit, then what it does for you is that it's the same as computing phi in some arbitrary background of chi and just shifting chi by bit. So this is maybe not super surprising because Q and chi are conjugate pairs, but it's still a nice result that somehow resonates with this fact here that if we have a correlator of some hard fields in a given vacuum labeled by Goldstone boson C, if we add a soft graviton, then this amounts to changing C. So I'm not claiming that this has anything to do that this is some dual to gravity. I mean, this is not dual, but it looks at least very reminiscent. So again, so the point I want to stress again, so we have these two sectors, the Q sector with unfortunately only, the electric sector with unfortunately only Gaussian correlators, the chi sector, which looks a lot like it could correspond to the soft sector in a potential dual. Maybe, so can we make this a bit more precise? And yes, you can in a nice setup, which is gravity in 3-dimensional flat space. So this is now, I'm switching now gears. This is the other paper I mentioned from in the very beginning, just a little piece of it to see these magnetic theories arising in gravity. And we can see explicitly that they describe some soft sector of gravity in this case. Okay, but maybe I'll stop here for a moment. Any questions so far?
Maybe I could ask the following question. The beta that you have introduced, this inverse temperature, can one see it as
I think formally, so what I can at least tell you that in these computations, we checked explicitly that if you compute the thermal correlator by trace e to the minus beta h, trace e to minus beta h with these insertions in there, it's the same as if you do your prescription, you compactify time with periodicity. You go to Euclidean time, compactify with periodicity beta. So at least in this setup, it agrees. Yeah, it's right. If you at least on this formal level of the computation, it seems to match. I don't have any good physical interpretation of this. Okay, so let's switch gears, discuss 3D flat space gravity. So just a quick 3D flat space gravity reminder. So boundary gauge is characterized by these two functions, P and J. Notice that this is, oh, sorry, before I start here, maybe, I mean, I could also, I'm good with fun. Okay, otherwise I could just drop this and go to the, okay, then, so we have this boundary gauge in 3D. You can write exactly like this. There's no series expansions in R, no series expansion in R. We have two free functions, P and J, in this gauge. And in this gauge, the Einstein equation, they look very similar, so very simple. So DUP, so it's just these two equations, which look like conservation equations for P and J. And indeed, what you find is that P is a time-independent function, and J has this very simple form. You can you can also look at the symmetries preserving this line element, and what you will find is that they will keep the form of the line element, but change P and J in this way. So you have some super translations looking like this, and super rotations, which are just diffeomorphisms on the circle in 3 dimensions. So P and J transform in this slightly complicated but still very compact way that you can understand in a nice group from group theory very nicely. Namely, you can show that P and J fall into the co-adjoint orbits of BMS3. So this is Yannick mentioned this briefly on I mean in a different setup, but in his talk on Monday. So we have these co-adjoint representations. So P and J form co-adjoint representations of the BMS group. So what does this mean in practice? So take Minkowski space. So P is minus 1 over 16 2 pi g. J equals 0, and then apply these transformations. Apply a super translation or a super rotation, and you will find that you will get a P of theta that is parameterized, of course, by the BMS transformation you applied, and it has this very compact looking form. So this describes, so we can describe the orbits of Minkowski space in this way. The orbit of Minkowski space, you can label it, you can call it BMS3 over ISO 2,1. Why this quotient? Of course, because ISO 2,1 is the Poincare, the three-dimensional Poincare group, which leaves the Minkowski space invariant, right? So if I apply Poincare transformation, it doesn't do anything. This is related to the fact that here, so maybe you notice there's an SO 2,1 part in here, which is related to the fact that the Schwarzian is SO 2,1 invariant. Okay, so there's much more to say about 3D gravity, but what I want to focus on is that you can reduce the dynamics of 3D gravity to a two-dimensional action that you can imagine, that you can think of as living on scry. And this 2D action is on the co-adjoint orbits, defined on the co-adjoint orbits of BMS3. This was discussed in these two papers, but the procedure goes back to some works by Cousin, Renaud, and Van Driel, and that was revisited by Jordan and Christian some years ago. So what's the procedure? Yeah, sorry.
Would you have automatically gotten a Carrollian action in any number of dimensions, or is this something special about 3 dimensions?
I think so. In this BMS geometric action has been constructed in 4 dimensions by Glenn and Romain and Kevin, and I think you get the same. Yeah. So, what's the procedure? You write the Einstein-Hilbert action in the first order form. It looks a bit like a Chern-Simons theory. But what is very nice is that you can solve, there's a constraint that you can explicitly solve, which is that the constraint is purely spatial constraint, the R-phi constraint. You can solve it explicitly. You can write the solution in terms of group elements on time and space, some group elements of ISO 2,1. You plug in the solution of the constraints, you impose asymptotically flat boundary conditions, and this is the reduced action that you get on the boundary. This was done by in this paper by Max and Wout a couple of years ago. But what we realized is that you can write it in this very nicely looking way that you should recognize now as a magnetic Carrollian theory. So we have this pair. So let me unpack this for you. The action itself depends on 2 fields, alpha and F. But you can write, so you can define this quantity P of F written in this way. And then in terms of this quantity P, the action looks like this, but you should always remember that P is a constraint field. So alpha and P are conjugate pairs, and the Hamiltonian is just P. So this is immediately, obviously, a Carrollian invariant action. This action has a global symmetry, which is BMS, not surprisingly, BMS3. These are the charges for BMS3. And expanding the charges into modes, you find that they indeed form the BMS3 algebra at this, quotation mark, central charge. It's a different central charge than the Virasoro central charge. The equations of motion of this theory are just the conservation of the BMS3 charges. So you see immediately that if I vary with respect to alpha, P is conserved, which tells you that this charge is conserved. And the other equation of motion is just telling you that this charge is conserved. So these equations of motion telling you the conservation of charges is very reminiscent of hydrodynamic theories. So you can think of this as some kind of hydrodynamics, Carrollian hydrodynamics. Carrollian hydrodynamics. Okay, now just let's apply these different points I told you about in this last slide, on the magnetic Carrollian theories to this action and see what we get. So we can expand this in. We have again these. Before we expanded into a basis of chi fields, which are now this field P. So these are eigenstates of the Hamiltonian. We can compute transition amplitudes between these fields, and we see that, of course, since there's nothing happening, there are no dynamical degrees of freedom in this case, so P is conserved. And the only thing that you get is some phase. You can compute the partition function at some inverse, at the inverse temperature, beta minus 1. So this is it. Here's our, so we trace over all the states P. The measure of this path integral is fixed by the fact that this is a co-adjoint orbit of BMS. So if I write it like this, you should always remember that, in fact, the fundamental variables are the f's, right? So this is a path integral over the f's. What you get, since these are eigenstates, you get again this big IR divergence, and then just a path integral. Okay, again, you should think of this as f's over the f over this Schwarzian action. So turns out the partition function of this BMS3 geometric action that we have here is given by an IR divergence times the partition function of the Schwarzian action computed by Stanford and Witten. So here you see this finite piece that you get from here. This is the famous 3/2 that you get from the one loop corrections around the saddle point. So this is the saddle point, which is just Minkowski space. And this here describes the fluctuations of the super translation, of the, in this case, super rotations around Minkowski space. Okay, so again, the upshot of this is, in the spirit of this talk, I wanted to convince you that the magnetic Carrollian action has something to do with soft modes. We can see this very explicitly in 3D gravity. In some sense, because there is only the soft modes, there's nothing more. But what you can do is, and what we do in the paper, you can add matter, you can construct a symmetry algebra in the presence of matter, you can define also some kind of soft theorems in the presence of matter. But since it's a bit outside of the scope of this talk, I just refer you to this talk by Stefan in the online seminar series. Okay, and with this I want to conclude. So I hope I brought across the message that these quantum Carrollian theories, not talking about conformal Carrollian theories, they exhibit features that you would expect for a holographic dual, dependent distributional correlators, which should correspond to the hard modes. Magnetic sectors describes time-independent correlators corresponding to the soft modes. We saw this a bit more explicitly in the 3D gravity case, but so far, the problem is that these models are definitely too simple, right? We only have these Gaussian correlators, and if we want to make progress, I think we should try to construct a model where we have also not these non-Gaussian correlators in electric Carrollian theories. So let me end by saying that some shapes, if you wish, are emerging, but there's still a lot of work to do. Yeah, thank you very much.
Thank you, Jakob. Are there more questions, comments? Massimo?
I don't quite understand the logic of trying to construct a Carrollian.
Yes.
It seems something unrelated.
Well, okay, so in the gravity, okay, for the, I think for scattering amplitudes, it's a fair question to see whether you can definitely write down correlation functions of such a theory, right? And for scattering amplitudes, I think it's a fair question to see whether you can reproduce some of these structures. But in a non-perturbative setup, yeah, as I said before, I'm still a bit confused about the setups, about the different roles of time in this case. Yes, I mean, just.
Maybe it's useful to remember that conformal Carroll is isomorphic to Bianchi, and therefore, since we are interested in Bianchi for different things, maybe it's not so strange that one works on time conformal Carroll in different versions.
So maybe just a comment to come back to the question of Massimo is that you can reinterpret this constraints equation as Cry. So the
Yeah.
It just might be a question. So we're introducing the equation theory, but did you think about constraints the life as something greater?
No, we didn't. I mean, we talked about this yesterday. No, we didn't think of this. We tried to think of these models as really defined on their own without any reference to the fact that they derive from C to zero limits. I don't know. Maybe it's a smarter way to do it. Yeah.
Actually, this is a historical question, but I remember that many, many years ago, there were people who tried to open up the light cone and work around C equal to zero. I don't know. Is there any relation between this work done long ago and Carrollian theory, or it's completely orthogonal?
You mean this ultra-local quantum field theories? Yeah, can't remember the name, but there has been some work on ultra-local. Some people tried to define quantum field theories more rigorously, coming from basically what we would now call these electric Carrollian theories. Maybe somebody else remembers the name. But I'm not sure whether this has led anywhere. So we try to think of this kind of from scratch.
Maybe related to.
Yeah.
Open up the light cone.
Yep. Yeah. Yes, yes. Very good. We had some discussion about this yesterday. Maybe you can use these kinds of things as regulators to regulate these theories. The fact that you have these post-Carrollian expansions, that's what Daniel made me aware of yesterday. Yeah.
If we just take some scattering amplitudes in GR or GR coupled matter, let's just say tree level, that has some symmetries which I would think would be Carrollian symmetries. So could you use scattering amplitudes to just construct Carrollian invariant correlation functions, even if you don't know how to derive them from an action?
Yeah, this is what I think the map that Laura, Yannick, and Romain and Adrien came up with. It gives you correlation functions that transform exactly in this Carrollian way.
Yeah.
But
and so maybe one goal would be to try to find some action that defines it intrinsically. Is that?
I would be happy just finding some action that gives me a 3-point function. A Carrollian 3-point function is not 0.
Yeah, but presumably these are non-local on the sphere, right? You would need a non-local action on the. You can't have all the points decoupled, right?
Yeah, so this, right. With these very simple theories that I showed you in the very beginning, I agree. I mean, all the correlation functions will be just localized in 1 point. So what we hoped was if we couple this electric sector with these delta functions to the magnetic sectors, that we would come up with that points would start talking to each other. But apparently the model we looked at was too simple. So, I mean, the other option, of course, would be that these actions that we're looking for are non-local. Yeah, but this would maybe not be I mean, maybe it's where we have to go, but would not be so nice, I suppose. Yes. You don't have to take n limit. So if I think the point is that I take the 4-point amplitude in gravity, I apply this integral transform by an integral transform, and I will get an object that depends on u and x, and transforms so you can think of it as a representation. Okay, let me phrase it like this. There are I can write scry. I can write scry as ISO 3,1 over some 7-dimensional subgroup, right? What I can do is I can induce a representation on scry from the 7-dimensional subgroup. I can induce a representation of ISO 3,1 from this 7-dimensional subgroup, and I will get an object that depends on u and xi. So and these fields will transform under Poincaré exactly, but they are rather 3-dimensional. I mean, this is an object that lives on 3 dimensions, so it's this is what we would like to call a conformal Carrollian field. So if I take the 4-point scattering amplitude, so these will be labeled by some conformal weight and some spin. And if I take your 4-point graviton scattering amplitude, I apply the integral transform of one of these 2 papers that I showed you before, then this will transform exactly like as if it were a 4-point function of 4 Carrollian scalars with j plus minus 2. So this is the object that we're trying to reconstruct somehow from independently from a conformal Carrollian theory. At the end, it depends on u and x. I mean, yeah, x. So the parameter, okay. The transformation is very easy in some sense. So if the transformation that you have to apply to each leg is, say, you parameterize your momenta by omega qm, where q mu, where q nu is some null vector, then the integral transform that you have to apply to each leg is just a Fourier transform. And here you have your 4-point graviton scattering amplitudes that depends on omega and xi. So this is kind of the dictionary that was proposed in these 2 papers.
But it's much simpler than that, right? I mean, Paolo, this is just going from momentum basis to position basis.
Yes.
This is just a Fourier transform.
Just a Fourier.
I'm here. I'm on your right.
Yeah, Hill's case is simplest. You still retain the Park-Taylor factor of MHV, but the edges are diffused with sine functions. Well, that's a transform.
Have you thought about studying some kind of string theory amplitudes in a Carrollian background, which might be naturally non-local, so it might be regulated?
I didn't, but I should say there's been a lot of work in on these two-dimensional Carrollian amplitudes by Daniel and Arjun and other people. Maybe I think they have thought about this. But I don't have anything to say. Yeah. Oh yeah, sorry. Yeah, we heard about this Monday. Yeah, sorry.
Further questions? All right, so I think we can close it here and thank Jakob again.